You know, for a self-driving car to actually navigate our world, it can't just see a flat picture, right? It needs to build this rich, three-dimensional model of everything around it. We're talking other cars, pedestrians, the road, the whole 9 yards. And it has to do it instantly. This whole idea of real-time 3D world building is one of the biggest hurdles in the race for full autonomy. So today, we're going to dive deep and break down the incredible evolution of the tech that's making it all happen.
All right, so here's the game plan. We'll kick things off with the old-school geometric methods, the foundation. Then we'll jump into the absolute revolution that was NERF. After that, we'll see how 3D Gaussian splatting came along and basically unlocked real-time performance. And finally, we'll put all this amazing tech to the ultimate test, autonomous driving, before we peek into the future.
So let's rewind a bit. Before deep learning completely changed the game, the world of 3D reconstruction, it was all about pure geometry. I mean, these classical methods, they really laid the foundation for everything, and I mean everything that followed. Okay, so the big players back then were techniques called structure from motion, or SFM, and multi-view stereo, MVS. And the core idea is actually pretty brilliant. It's like this. If you snap a bunch of photos of, say, a fire hydrant from different spots, your algorithm can find the same points on the hydrant in each picture. Then, through some clever math, basically triangulation, it can figure out exactly where those points are in 3D space. You do that enough times, and bam, you start building a 3D model, like a point cloud or a mesh, of the whole scene.
But, and this is a huge but, these methods have a serious Achilles heel. When you think about what a self-driving car has to deal with, the real world is a total nightmare for these old techniques. I'm talking about blank walls with no texture, shiny reflections on a wet road that just get totally confused. And don't even get me started on moving objects, like a person walking across the street. The classical methods just fall apart. They're way too slow and way too fragile for the kind of split-second decisions a car needs to make.
So this major weakness, this brittleness, it forced a complete rethink of the entire problem. Researchers basically had to go back to the drawing board. They started asking, okay, instead of carefully building this geometric puzzle piece by piece, what if we could just teach a neural network to see and understand an entire 3D scene all at once?
And that question, that led to something called neural radiance fields, or NERF for short. And let me tell you, NERF wasn't just some small step forward. As this quote says, it was a quantum leap. Suddenly, we could create these incredibly photorealistic new views of a scene. The level of detail was it was something nobody had ever seen before.
So you're probably wondering, how on earth does it work? Well, a NERF is completely different. It doesn't store a bunch of points or triangles like the old methods. Instead, it's a deep neural network that basically learns a continuous function of the scene. Think of it like a magic black box. You ask it, hey, at this exact 3D coordinate, looking from this direction, what do I see? And it spits out a color and a density. It literally learns this continuous, volumetric field of the entire space. It's wild. Okay, so this slide gets to the absolute heart of the matter. It's this fundamental difference in how the scene is represented. The classical methods are explicit. They store actual points and meshes. You can point to the geometry. But NERF, it's implicit. The whole scene is just encoded in the weights of a neural network. That's the secret sauce that lets it capture all this incredible detail, like complex lighting and soft shadows. But there's always a but, right? It comes at a massive cost. Look at the bottom there. It is painfully slow. We're talking slow to train and slow to render.
And yeah, that speed problem, it was a total deal breaker. I mean, an autonomous car has to make decisions in milliseconds. A rendering time that takes minutes, that's a complete non-starter. So this created a huge push, a real-time imperative for the whole field. The challenge was clear. We need the stunning quality of NERF, but we need it at the speed of the old-school methods. How do we get there?
And then enter 3D Gaussian splatting, or 3GS. This was the breakthrough everyone was waiting for. It was designed to give us the best of both worlds. The idea was to create a representation that was explicit, so easy and fast to render, but that you could still train and optimize with all the power of deep learning to get that gorgeous NERF-level quality.
So instead of this implicit neural network or a rigid mesh, 3DGS represents the scene as a cloud of millions of tiny, soft, 3D blobs called Gaussians. The best way to think about it is like this. Imagine each Gaussian is a tiny, semi-transparent, colored puff of smoke. And by splatting, which is really just a fancy word for projecting,
These millions of puffs onto your screen, you can render a stunningly realistic image, and you can do it incredibly fast. And this table really tells the whole story. Just look at that 3D column. Real-time rendering speed? Check. Fast training? Check. Super high realism? Double check. You get it all in one package. It completely shattered that old trade-off between quality and speed that had basically defined the entire field for years. This was the game changer.
All right, so we've got this incredible new tool. Now for the real test. Let's see how it holds up in the ultimate proving ground, the chaotic, unpredictable world of a self-driving car.
You know, this whole journey really started with foundational ideas like the architecture you're seeing here. It's called an encoder-decoder. Basically, it takes a 2D image. The encoder part squishes it down into this compact code, like the digital essence of the object, and then the decoder part rebuilds it, but this time as a 3D grid of voxels. This was a huge first step in teaching a machine to see in 3D from a flat image.
And this really lays out the specific monsters that a self-driving car's perception system has to slay every single second. First, speed. It has to be real-time, no excuses. Second, it has to deal with moving stuff, cars, people, which basically adds time as a fourth dimension to the problem. Then you've got all the tricky surfaces, like shiny, reflective car paint or see-through glass. And finally, it has to be smart about things it can't see, handling occlusions and reasoning about what's hidden.
Okay, now here's where it gets really cool. We're now seeing specialized models being built to tackle each one of these challenges head-on. Need speed? We've got feed-forward models that just spit out the 3D geometry at over 20 frames per second. Moving objects? No problem. There are techniques that actually model how the Gaussians themselves move over time, tracking everything. Reflections? Specialized models can now intelligently separate the reflection from the actual car paint. And seeing through glass? Get this. Some new methods are even learning to model the physics of how light actually bends and refracts. It's just incredible.
I mean, the progress has been absolutely breathtaking. We've gone from these slow, fragile models to real-time dynamic systems that are even starting to understand physics. But of course, the journey isn't over. The road ahead still has some major hurdles. So if there's one big idea to take away from all this, it's this massive shift in thinking. We've moved away from slowly solving these geometric puzzles, piece by piece. Now we're in a world of end-to-end feed-forward inference. That means a single powerful network can look at a scene and, in basically one shot, figure out the 3D structure. That's the paradigm shift that really unlocked real-time performance.
So let's leave it with this final thought. We've made these unbelievable leaps in solving the problem of seeing the world in 3D. The models can build these stunningly realistic dynamic maps in the blink of an eye. But here's the thing. Seeing isn't the same as understanding. Now that the car can build this perfect picture of the world, the next great frontier is teaching it how to truly reason about it, to get a handle on things like physics, cause and effect, and what other drivers might do next. So what's the next bottleneck? Is it better data, faster hardware, or is it all down to a breakthrough in algorithmic reasoning?